Now, first, of course, I should say that this talk is not entirely only written by myself. I shamelessly borrowed, stole, copied a bunch of slides from a bunch of very close friends, and in particular from Jack Radcliffe, Benito Marcote, Mark Katanis, Art Keimpema. So I should thank these guys for a couple of slides that were just very nicely illustrating what I wanted to show. So, very long baseline interferometry. What is it, and why do we even bother? Let me go back a second and remind you of this particular slide on resolution, which I more or less flipped by. So it's lambda over d, right? It's the wavelength over the diameter of your dish. Now let's assume we're observing at my favorite frequency, which is 1.4 gigahertz or 18 centimeters wavelength. And then let's assume we're observing with one of my favorite stations, which is the Effelsberg telescope, which is one of the biggest, which is 100 meters in diameter. If you do the maths, you end up at roughly 6 arc minutes full 6 arc minutes, full width at half maximum. So your beam size is about 6 arc minutes. What does this actually mean? Let's take a nice SDSS optical image, and let's take a look at NGC 600. And this particular image here is some 12 arc minutes across. So we stick the Effelsberg beam on top, and Effelsberg will entirely cover this galaxy. You're going to see the galaxy, but you're not going to be able to say anything about what is happening inside the galaxy, right? You have one blob, and so this is your 6 arc minutes. So what we can do, we can of course then go to the UGMRT, which is the interferometer with a baseline length max of roughly 25 kilometers. This brings us down to 1.5 arc seconds. So that's already a huge improvement. Going back to this particular image, bloody hell, my arrow disappeared. So this is, the small red dot here. You'd think PDF doesn't screw you up, but it does. So there is an arrow here, which points at this very small little full width at half maximum, so beam size of the UGMRT. So with this, of course, you can then try and map out the galaxy, and you can tell something about what is happening where in this particular galaxy, right? You can take a look at the spiral arms, you can study what is happening, you can study magnetic fields in the spiral arms, whatnot. You can actually dissect this particular galaxy. So you wonder, isn't that good enough? We can actually, dissect the galaxy, great stuff. But then let's go further. Let's take a look at something like this. This is a gravitational lens. In here in the middle, there is a big chunk of matter, mostly dark matter. And then you have these beautiful arcs, and this is a gravitational lens. So there is a point source in the background of this particular foreground cluster, whatever it is, which is lensing a point source. And as you can see, this particular image here is now 0.9 arc seconds across. If we stick the UGMRT beam onto this, this tiny red circle that we saw before, you get that the UGMRT beam on a 25 kilometer baseline covers this part of the sky entirely. So you will not be able to resolve this. There's no way. So that's why there is VLBI, and my favorite array here is the European VLBI array, VLBI network. And this is just stations all across the globe. Well, of course, they pointed to RC, which is no more, never mind. So this is VLBI. You're taking your dishes not just on 25 kilometer baselines, but you put your dishes all across the globe, which then gives you access to 10,000 kilometer baselines. So effectively, you are synthesizing a dish which has the diameter of 10,000 kilometers. You can, of course, go further. You can also send a satellite into space, which is then called space VLBI. Then you go to 100,000 of kilometers. But let's not go that far just yet. So with this 10,000 kilometers, 18 centimeter wavelength, we're now talking 4 milliarc second resolution. Hey, this one gave me an error. So here, this is now the VLBI beam, right? So this is 4 milliarc seconds, and then of course, you can put, you of course observe the entire thing, and then you make an image. And since your beam is so small, you're actually resolving this arc. So this is why we want to do VLBI. We want to go further. We want to go beyond 25 kilometers. We want to go beyond the connected interferometers. We want to go to VLBI to do this sort of thing. Now, for FRBs, this is important and in particular very interesting, because with FRBs, to understand what FRBs are, there is of course the question of what host galaxies there are. And for host galaxy association, arc second level is definitely good enough. Then you can do the statistics. Are we in ellipticals? Are we in spirals? Are we in, and what sort of galaxies we're in? But that only tells you the galaxy. It doesn't tell you what's happening in the local environment of the FRB. For this sort of thing, you want to go to VLBI, and this is one of Benito Marcota's localizations, where he pinpointed the FRB down to this region out here in the spiral galaxy. You know, this is not the VLBI beam. This is a factor of, I don't know, 10,000 bigger than the VLBI beam, just to show you that it was pinpointed to this location out here. And if you then actually zoom in, right, this is the same location here, and then you zoom in, and the green now is the VLBI localization at the edge, at the end of this funny shaped star-forming region. And you can actually say, okay, there is something here, but it's a few hundred parsecs away from the star-forming region. So you can actually tell, okay, we're not inside the star-forming region, we're close to it. For this sort of thing, we definitely need VLBI. Similar localization is something like this, where we managed to pinpoint an FRB to the globular cluster that Kaustup already mentioned yesterday, which is, you know, which puzzled everybody. How do you get something that should be a magnetar or a young neutron star into a globular cluster? And this is also only possible with VLBI, right? So here, the red circle is actually where the FRB comes from. So we cannot only say it's in the globular cluster, we can say where it is in the globular cluster. We can say it's some 2 parsec away from the globular cluster core, which then tells you, okay, what do we have in a globular cluster core? Do we have compact objects around there? So you can actually start to really say, what do we have in the local vicinity, in the local environment of the FRB? That's only possible with VLBI. Now the localization here, and this is already something that illustrates a bit of a problem with localizing FRBs, because you know, we have a very sparsely filled UV plane, which we'll get to again later on, and you sometimes all you get is a dirty image like this, where you cannot tell which of these side lobes is the location of the FRB. So in this case, what we do is we fit a 2-dimensional Gaussian to this cross pattern, and we have a region. Right? So this is one of the issues with FRB localization, because you have a snapshot, and FRB is a millisecond, right? We don't have Earth rotation synthesis helping us with the single burst. We have a millisecond snapshot of the sky, so we have pretty much nothing to work with. But still, you can manage to then localize it. And in this particular case, this was a localization to the faintest galaxy at this point. I think at least luminous at this point. Now then, this is work by a student in Amsterdam, Alexander Morianu. Because here, what we also do with VLBI is we don't just localize the bursts themselves, but we're always looking for if there is a compact persistent radio source at the location of the FRB. Most FRBs do not have a persistent counterpart. There is pretty much nothing, at least, well, those that we have localized. But here, in this particular case, there is a persistent source. And then you can, of course, think again what might potentially cause this persistent radio source. Is there a question? Yes. No, this is really just, what we do here is we fit a 2D Gaussian distribution to this cross pattern, and that's just the 2-3 sigma regions of this Gaussian.
Okay. Yeah, it doesn't have to do anything with the instrument or the...
No. Well, I mean, it does have to do with the instrument in the sense that, you know, the size of this cross pattern is definitely determined by your instrument. In that sense, yes. But, I mean,
not
you know,
the PSF or anything like that.
Sorry?
But not the PSF or anything like that.
Well, what you see here is the PSF, right? So this is the dirty image. So in this case, and we also do this in the tutorial, in most cases with FRBs, we're not working with clean images because that would just be cheating. Because, you know, if you have a dirty image like this, where are you going to clean? Where is the FRB? You have no bloody idea. So that's why here we just fit this 2D Gaussian. And, you know, it is related because the cross pattern is determined by your point spread function. Sorry?
Hello. Yeah, if there is a bright source nearby and it falls into the side lobe, then how will you be able to distinguish because the side lobe situation
so in VLBI, you typically don't have that problem because your field of view is very small. And it's never happened that we had a bright source so close that it would mess up our beams. But then, yes, you would probably have to do some peeling, but typically in VLBI, your field of view is so small that you rarely ever have a bright source so close that it messes up, that it gets into your side lobes. Luckily, we don't have to deal with that. Okay. Not yet, anyway.
Thank you.
So yeah, here we have a persistent radio source, a persistent counterpart. And then this is also, I'm just flipping this up because this is the data set that we will work with in the tutorial, where we have the localization of the FRB here, and then we have the deep image. In this particular case, there was no persistent radio source counterpart, but there is something at 22 gigahertz observed by the VLA, but this is associated with star formation, so there's no compact source. Just flipping this up because this is what we'll work with later on. Now, so much for the intro to why we actually want to do VLBI and why we want to do VLBI on FRBs, all about localization and local environment. But let's actually look at how VLBI works. Just to compare, first of all, connected interferometers like the GMRT or VLA, those systems are connected because they typically all run on the same clock. They run all through the same electronics. The baseline length of some tens of kilometers mean that all of the dishes see the same part of the sky. And of course, that's pretty much all I had to say here. But in comparison to very long base interferometry, we have a very inhomogeneous array, right? So each of those stations might run their own, their own control system. Each of the stations has, in particular, their own clock. You may think clocks are all the same, but no. There can be offsets between mazes by, on the order of, well, sometimes it can be seconds, but typically it's on the order of milliseconds. But if we want to do things coherently, we need to have nanosecond accuracy in our arrival times. And of course, the long baselines of 10,000 kilometers, or even just a few thousand kilometers, they mean they all see very different skies. And why am I pointing out the different skies? So here is, another nice schematic view. You have your dishes, and then of course we have up here, we have the ionosphere, which is turbulent, and this dish certainly looks through different parts of the troposphere, ionosphere than this array over here. So we need to actually take the sky into account. There are dispersive and non-dispersive effects that happen in the ionosphere and the troposphere, and those need to be taken into account. The different clocks need to be taken into account. So we need to actually figure out how relatively wrong are the different clocks at different stations. So all these things need to be taken into account to actually be able to coherently correlate or get a nice coherent fringe in our correlations. Just a very quick reminder, and then I'll also have a very quick question. So we have our visibility function, right? Which is just the Fourier transform of the sky. As I showed you earlier, in the general case, we're looking in the direction of W, or S0, as I called it, and we have a source in the direction of S. Now, what actually happens if S and W, if they're the same, if we have a source in the very direction of W or S0, so if there's no offset between pointing center and source, what happens in this case here? Remember the direction cosines, right? L, M, and N are cosine alpha, cosine beta, cosine gamma. Can anybody tell me what happens if S and W are parallel? And these angles here are, what are they then? 90 degrees, okay. And these are direction cosines, right? What happens at cosine of 90? 0, exactly. Which means this term here is 0. So we have a phase of 0, a point source at the phase tracking center has a phase of 0. So we can more or less, if everything is good, we can do the inverse Fourier transform. Keep this in mind. A point source in the phase tracking center has a phase of 0. All right, we'll get to this again in a bit. So this takes us directly to the interferometer measurement equation, because we have certain visibilities that we observe, and we have the true visibilities, and then we have all sorts of rubbish that actually compromises or affects our true visibilities. There is baseline-based errors, so there can be some delay errors or whatever per baseline. There is, of course, the bandpass. Each of the different frequency ranges has a filter and a bandpass response, both in amplitude and phase, so it's a complex thing. We have gains and amplitudes also imposed by the troposphere and ionosphere. We have instrumental polarization. We have elevation errors. We have all sorts of different things that go into our observed visibilities. Luckily, because what we want to get to is the true visibilities before we can actually do our inverse Fourier transform to actually image anything. So we need to take care of these things, but nicely enough, we can decompose these, right? I was talking about phases before, but in the end, the phases is nothing else than just delays, right? Because it's all about different path lengths, and then, because of the path lengths, you end up at a different phase. So our observed delay can be decomposed into, first of all, a geometric term, right? Because that's just geometry, because one dish is here, one dish is there, that's geometry. Then we have source structure, right? This is actually what I showed before. If you have your S, it's distributed, and you have different, it might be broader, and you have source structure that adds delays in there. Then, of course, we have the propagation effects. We have the troposphere, we have the ionosphere. All this adds, as a function of frequency, adds different delays, i.e. translates directly into our phases. And then we have instrumental effects, because the different parts of our observed frequency go through different electronics. All this needs to be taken care of. And of course, there's whatever other noise that we could think of. And here we go. Here are our phases. If you look at, so this is now as a function of time, we have our phases as such. And as you can see, this is sort of as a function of frequency. No, this is two polarizations and different frequencies. This is why this is so broad, and the phases are, there is structure to the phases, but as I said earlier, for a point source in the phase tracking center, we want to have our phases all zero, right? So this is far from zero. This is wrapping around. And then, of course, we have the delays, which is just the phase as a function of frequency. The phases are also frequency dependent in this particular case, and we have the phases. It's the rates, the phases also change as a function of time. All this you see in this somewhat of a mess. What we want for a point-like source at the phase center, we want the phases to be zero. So this is why we go into calibration. And the whole assumption here is with the calibration is that we're observing a bright source. That is our calibrator. It is a point source. It is at the phase tracking center. We look at our phases and we make sure that our phases are zero across time, the phases are zero across frequency, the phases are zero, just centered around zero generally. So that's why we have, typically, we observe our target, which might be, resolved or not resolved. We observe a close-by phase calibrator. I keep crapping on about the phase, but really VLBI is all about the phases, right? We have a phase calibrator, a point source close by, within 1 to max 3 degrees ideally, so very close to the source, because if you go further away, you see different parts of the atmosphere, because you want to calibrate your interferometer on this phase calibrator. You want to transfer them to the source, so it should be very close. They should see very similar skies. Then we have something that is called a fringe finder. It's a bright source. It's also a bandpass calibrator. We want to have something that is a flat spectrum source. And of course, if we want to do polarization observations, we want to observe a polarized source, we want to observe polarization calibrator. Ideally, it's non-polarized, but of course, you can also use something where you know the polarization state. If you know to what degree it's linearly or circularly polarized, you can then calibrate your data to look the same. Now, a typical VLBI observation is sort of set up like this. So the blue bits are the phase calibrator scans, the green bits are the target scans. For the FRB stuff, we often observe what we call a check source, and then we have a fringe finder, and if we choose to do so, we take a polarization calibrator. In terms of amplitudes, right, this is all in relative amplitudes. So your fringe finder ideally is a nice and bright source, and often we observe the fringe finder source or the bandpass calibrator source in the very beginning and at the very end, just to see how the system evolved during the observations. And then we do this cycling between target, where, at L band, I would typically spend 5 to 6 minutes on the source on the target. And then the phase calibrator, is typically, of course, brighter. It has a higher amplitude. Our target is typically faint, and you don't see much there, but the phase calibrator is bright, and you just cycle some, say, 2 minutes on the phase calibrator, 5 to 6 minutes on the target, because the coherence length at L band is, some 5 to 10 minutes, depending a bit on the weather. And then in between, we often also observe a so-called check source. That is a source that is close to our target and a source for which we know the coordinates well, because what we want to do is we want to check our astrometry. For VLBI and FRBs, it's all about localization. And if our astrometry is crap, then of course our localization is crap. And if we have a check source for which we know the astrometry good enough, we can check if our calibration is good enough, if we suffer from any systematics, because if we measure a systematically different position for the check source, we know that our localization of the FRB is going to be affected in a similar way. So this is just, the check source is mostly just a sanity check source that our astrometry is correct. And then, yes, in terms of phases, typically, the phases for the phase calibrator in the beginning before calibration, they go around somewhat, but they should all center around zeros. Typically, there is structure to it. For the target, you typically have the phases all over the place because, your target might have structure. It might not be in the center of the beam. So you don't expect it to be just around a particular, particular value. So effectively, you just beam back and forth, right? You have your target somewhere. Within a few degrees, you have your phase calibrator. You have your flux calibrator somewhere. In this particular scheme, it looks like the flux calibrator is at a very low elevation. That is not the case. It's just to show that it can be far away, but it doesn't have to be low elevation, right? Okay. Of course, then once you've done your observations with VLBI, you need to correlate your data somewhere. And with the EVN, we do this at Jive on the SFXC correlator. And the data are typically streamed from the stations to the correlator because, for GMRT, VLA, they all have the correlation facilities on site, so you don't need to stream it anywhere. And then, there's a whole bunch of architecture that goes through where you try to correct for the geometry and you try to correct for all sorts of spectral effects, which is why you have these window overlapping functions and whatnot. And in the end, so SFXC, I should actually say this is the super FX correlator, and FX because you do the Fourier transform first and then you cross correlate. You can also do the inverse. You can cross correlate and then Fourier transform, but we do FX in this particular case. We do the cross multiplication. So we do the whole FFTing. We then do the cross multiplication. Then we accumulate, where accumulate means we're just averaging in time, right? Say we want to just have 2-second integrations and a particular frequency resolution. This is what's happening in the end. Now, for FRBs and pulsars, there is another step, which is called pulsar binning or gating. I hope you can kind of see that there are some pulses here. It doesn't come up too well, but the point here being, as you know, pulsars are dispersed, so are FRBs. So first of all, we need to, of course, de-disperse our data such that we actually see any pulses. So here I just took 1933 plus 16 because that's one of my favorites. So this is also what's happening then during correlation. We actually de-disperse the data during correlation, and because a pulsar and also an FRB, they're of course off most of the time, right? So all this noise, we don't actually want to correlate that. So what we do is we gate it, which means that effectively we only take the data off the pulsar or the FRB when the pulsar or the FRB are actually on. So this is called gating, and we only accumulate the data when the source is on. And this is also the same thing for FRBs. We don't correlate. Say we spend some 3 hours on the source, we have one burst, which is a millisecond. We don't correlate this whole thing, right? If we want to see the FRB, because you won't see it. Right? We'll just bury it in the noise. So we only do the gating where we just take the 1 millisecond of data, which we then correlate. And in case you were wondering what the difference is between gating and binning, so gating means you have one gate around the pulse. But if you want to do binning, you can actually have, if you want, several gates across your pulse, which you then call bins. Why would you do this? In the case of pulsars, this is very interesting because if you have a pulsar which has structure in the profile, you can have phase-resolved astrometry of your pulsar, which is something which you do in scintillometry, where you then can try if you can actually see a phase offset between one part of the pulse and the other part of the pulse, and then you can do some astrometry on the pulse itself. Now, another issue with FRB localization is that in the beginning, when we have an FRB, we might have to, so typically we observe repeating FRBs, which were detected by chime. And the chime localization, if we have baseband data, is good to, 3, 4, 5, 6 arc minutes, which means, going again with the Effelsberg beam, because that's the biggest dish, we have a 6 arc minute beam and say our FRB is somewhere here. In initially, we have no idea where in our full field of view, because the full field of view is given by the Effelsberg beam, but our pencil beams, our resolution is still 4 milliarc seconds. We have initially no idea where inside this field of view of Effelsberg our FRB really is. We could, of course, try and image the entire field of view, but this is crazy because we got 4 milliarc second resolution across 6 arc minutes. So you'd have, I don't know how many billions of pixels in your image. This is not something we want to do. We do not want to image the entire field of view of, say, Effelsberg to do a first localization of our FRB. So what we do instead is called delay mapping. Because if you have in your field a bright source, we gated things, so we only have one bright source in the field, and you saw this cross pattern earlier, right? The cross pattern from if you have some fringes in a particular direction. This is also what we then make use of in delay mapping, because all we look for is sort of an overlapping region of different baselines where you have a higher signal to noise in the delays, right? So this is called delay mapping, where we get a first crude localization in our image, which is then good to 1 to roughly within an arc second. And then we can try and image that, and then we find the FRB itself. This is something I already alluded to a little bit before, our sparse UV coverage, right? So this is actually from an example from our tutorial that we're going to go through later. So this is the UV plane for 4 scans, but these scans here are actually 4 different bursts of one of the same FRB, right? They're just ordered in the measurement sets as scans, but they're actually the FRBs. So for a particular scan, this is the UV coverage, and you saw the point spread function of just a couple of points, how horrible it is. And this is what we then need to work with. And of course, if you are lucky, and we're using a data set where we were particularly lucky, we had in one observation, we had 13 bursts. And if you combine all these bursts, then if you go, you get a reasonable, what I would call a reasonable filling of the UV plane. And this is something that we'll tackle in the tutorial, and then you'll also see what those plots are all about. That's it.
Okay, time for questions.
Hi. Hi. All right. So this VLBI observation, it has to be synchronized. What kind of timestamp, like what we used for doing this timestamp for the data each time when you do the observation? Is it synchronized with any clock globally, or how it is doing?
Yeah. So the question was about synchronization and how this works. So the data are recorded. So first of all, of course, you have a maser at each station. So you do have a fairly accurate clock at each of the telescopes. And the way the clock or the stamping of the data works is that we're recording in what is called VDIF format. And in VDIF, you have a header for each package, right? So you have a different, well, how to best phrase this? So you have header information, right, for each package in your data. And this comes with a timestamp. And then you have sort of what is called frames. So you have timestamps on the full second, right? And then you have, say, 16,000 frames within this second. And then in the end, you can do the maths that, within this 1 second, I have 16,000 frames, and they are equispaced. And this is then how you get your clocks right, more or less. So this is how the stamping of the clock works, more or less in the data. I don't know if this more or less answers your question, or if it was actually a different one.
Yeah, in between observation, do you have to correct for the phase, like because that's
during the observation, you don't correct for any phase.
No, just observation. Then post observation, you are doing this correction, phase correction.
Yeah. So during the observations, you don't correct for any phases during the observation, right? So you just record. You have your timestamps, and then the correction in phase happens during the correlation after the observation offline, if you want.
Okay. Further questions? Can you?
Hello. Yeah. I have a follow-up on that question. During the observations, at least the individual centers, whichever are arrays, must be doing some phasing in to phase their local array, right?
Yes.
Not the global one, just.
No, exactly. So I mean, you can of course, yeah, on this one image, I think I had a little array. So you can, we also sometimes observe with the VLA, and then the VLA is phased up. And then for the VLA, if you sort of want to look at the observing schedule, if you observe with the VLA, you do need to also schedule phasing scans that you actually phase up the array, because after a while it's no longer coherent. So yeah, so you need to phase up your array. You have a phased up beam, which then is, but then you also need the phased up voltages, which you then send, and then you can do the correlations. Yes, and the same is going to happen. The same is happening with MACAT as well. The same is going to happen with the SK as well. That you get phased up stations.
Okay. Any more questions, discussions?
So I was curious if the phase calibration scheme is any different for VLBI, because you have so large baselines. You are sensitive. You are basically looking at a very small portion of the sky, which is highly turbulent. So is it enough to do like the normal phase calibration, where the source is still like somewhat apart from the like target? Can you comment on that? Is the phase calibration routine somewhat different than the standard ones than in the VLBI?
So no, it's the same as with the VLBA. No, so the VLBA and EVN, that's the same style of phase calibration. So
what I'm asking is from the standard imaging, like with normal, like say with the GMRT or the VLA.
Yeah.
Is there any difference in the phase calibration routine for the VLBI from the GMRT or the VLA?
I don't know. I've never done much VLBI. I've never done much phase calibration with the GMRT, I must say, but I don't think there is, because you also do phase cal target. Maybe I don't know if you do just longer cycle times. I'm not entirely sure.
Yeah. So the only difference is like those who have got the GMRT or any local telescope will find there is you do relative calibration, because you don't do absolute, because you don't need to know the absolute coordinate of the system, correct? So we have only one local phase reference. With respect to that, we are actually calibrating rest of the antenna. But doing correlation with, let's say, any European VLBI network, need to do absolute corrections, because you need to know the absolute location of GMRT and then correlate it. That is the extra thing which you never look at it when you actually
right.
the VLBI.
Yeah, that's right. So that's probably the biggest difference. Yeah, that of course, because with the connected interferometer, you know your location. You don't care too much. Well, you need to know the individual station location.
Yeah,
I guess.
but this is relative to some center location. You can make the array center 0.
Yeah, exactly.
Yeah,
but with global view, at least with the EVN, you do a similar thing in the sense that you just transfer all your stations to the center of Earth, right? So you actually correlate at the COE, and you do this transfer. This is sort of the geometry that you apply, the geometric term, that all stations are virtually moved to the COE, and this is where correlation happens. Then in a sense, you have a similar central point, yeah.
Thanks.
Thank you. I think the screen is gone.
Oh, did I bring it back up? Hang on, will you fix the mic?
Hello. The upper right that you are trying to show, the UV overlap region.
Go on.
No. Yeah, that cross section. Can you explain it a little better? I mean, I'm sorry, I'm unable to catch the point, because how does it work for FRB?
So you have the snapshot of the FRB, right? You have your visibilities. And what you're doing is, since if you have, any difference in DEC and RA is directly translating into a delay on a particular baseline, right? So what you do is, on the different baselines, you look in delay space, you look for a signal to noise maximum. And you do this for the different baselines and different delays on the different baselines. Then actually, if you then plot this up where you could be given a certain delay, so for a particular delay, and you get a certain region where your FRB could be. And if you have several baselines, these then will cross in a particular region. And in this region, more or less, you will have your FRB. And this is the region where you then put your correlation center, because you then do the proper correlation with this as the phase center. And then you can sort of see, you're not going to get a very good localization with this, but at least you're close. And then you can image this, and then you get a proper localization. But this is sort of the idea that for a baseline, you get probability region where it's going to be. And those then, hopefully, if you have several sensitive baselines, hopefully you get a good matching cross pattern of, say, 2 or 3 baselines.
Thank you.
Okay. Further questions? So we actually covered a lot. We came from tens of degree detection to milliarc seconds, so in 1.5 hours. Right? So yeah, there is so much to kind of absorb from your side, and there are coffee outside to also discuss. And so, but yeah, if you have something now, we can quickly take it up. Okay. Hopefully your downloading part is going on. Yeah. So I think there is a data already in the USB. The VLBI. Yeah. So whoever still actually they don't have the data in their local laptop, so you can actually borrow the USB. And so yeah. So just talk to Yash. Anybody who still want the VLBI data to be downloaded in the laptop, and take the USB.
Did anybody have trouble spinning up Casa in the Docker container? Did everybody try that? That they get a logger window popping up that the X11 forwarding has happened with Casa? Did anybody have issues with that? Sorry, come again? In MacBook, there's issues. All right. Okay, then we need to look into the Mac users. I have no idea, but okay, let's do it.
Is it like the graphics issue or something? Both. Yeah. UI issue. So it's not popping up.
Okay. Did you try the xhost plus local that you did, and you also ran the whole command, but it's still not popping up? Okay. Anybody a Mac user that can debug this? Because I have no idea. Okay. All right. We'll try and figure it out.
So how many of Mac users you have?
Yes. Hands up who's using a Mac? That's of order 10. Okay.
So you people can log into the NCRA and do it. Right?
Does it work for any Mac user?
But there is.
Did anybody get it to work? No. Okay, but haven't tried yet. Okay, that's fine. Okay. Yeah.
You can get the Casa.
Yeah, and I'll tell you, yeah, potentially for the Mac users, if Docker gives you too much pain, we can also just flip up how to actually install Casa locally on the Mac. Because it's essentially you're just downloading a tarball and you're untarring it, and then you have Casa installed. Probably, yeah.
We'll share a link on the Slack. So just try a Mac user. You can try that directly installing Casa tarball. Just see whether that works.